Bismillahirrahmanirrahim. Uh, Electromagnetic field theory, and today our topic is electric flux. The imaginary lines drawn from the surface of the charge, which indicates the direction of the electric field, are called electric flux lines, or the electric lines of force. Okay, so this is charge, and these imaginary lines are called the electric flux, and these electric flux are equal to the magnitude of the charge enclosed that surface. The electric flux density is defined as the electric flux or the electric lines of force passing through a unit area. So its unit will be coulomb per meter square, and it is a vector quantity, and it is always uh, directed in in the direction of electric field. So here is example of the electric flux density. This is a surface S, and we have taken a small surface ds, and the lines of force are passing through this surface. And if we have taken the small surface, then we will assume uh, d psi over ds. Okay, so that will be the flux density through a small surface area ds. Okay, and d is also equal to epsilon naught e. So it means the electric flux density is always in the direction of electric field. Okay, so we have to prove that how d is equal to epsilon naught e. We have taken a q, and these lines are actually the field, showing the field of that q. Okay, so d is equal to d in the direction of ar. Ar is the unit vector or the position vector directed from the q to the point of observation. Okay, so as we have taken the area for the q is a spherical area, so the area of the imaginary sphere will be a is equal to 4 pi r square. Okay, so d according to the definition, d is equal to psi over area. As I have already told you that psi is equal to, or the flux lines are equal to, the magnitude of the q. So q divided by a, putting the uh, value of the area, that is 4 pi r square. So we will get q over 4 pi r square in the direction of ar. As we have already proved, E is equal to q over 4 pi epsilon naught r square in the previous lecture. So multiplying both sides by epsilon naught, you will get epsilon naught E is equal to this. So this whole is equal to uh, the the d. Okay, here from here. So d is equal to epsilon naught E. Electric flux density due to volume charges. Uh, the volume charges we have proved in the last lecture, rho v over 4 pi epsilon naught r square. Okay, so again we have to multiply epsilon naught on both sides. Okay, so we will get epsilon naught e is equal to this. Again epsilon naught e is equal to d, so d will be equal to this, rho v dv over 4 pi r square ar. Okay, electric flux density due to line charges. As the electric field intensity due to the line charge is given by is this in the cylindrical coordinate system. So rho L over, again we have to multiply epsilon naught on both sides to get the d value for the line charges. These were the d value for the volume charges, and again, and now these are the d value for the line charges. Okay. Okay, now we have to find the d value or the flux value. We have to prove this psi n is equal to d dot ds. Okay, so This is actually the q, the position of the q charge. Okay, and this is the surface S, and we have taken the small surface ds, and the lines are passing through that surface. Okay, so and this is the point of observation, so the d will be directed from the q position to the point of observation. This is d. So now d have two components, one is this one and other is this one. Okay, so these are two the rectangular components of d. As this is theta, so the opposite, the vector that is opposite to theta is d sine theta, and this is actually the d cos theta. Okay, so uh, dn, this is actually the dn, the vector that is normal to the surface. Okay, so dn is applying the cos theta, dn over d, based by hypotenuse, and from that we get dn is equal to d cos theta. Okay, now from the definition of electric flux density, the flux lines are passing through a surface divided by the area of the surface. Okay, so dn is equal to the flux lines passing through a surface or the unit area. So d, from that we have the flux is equal to multiplying area on this side, so flux will be equal to dn into a. From that dn is equal to cos d cos theta, so putting d cos theta over here, d cos theta into area. Okay, now uh, d cos theta into area. Area is the small surface ds, so d cos theta into ds. So as dn is also a vector, from here dn is a vector, and the surface is also a vector. We have assumed the surface as a vector and its direction is always perpendicular to the surface. Okay, so if this is a surface, so its direction will be always this, perpendicular to the surface. If if this is the area or the surface, then the direction of the surface will be like that. Okay, okay, so these two are the vectors. So uh, we can say that d and ds both are in the form of dot product, because if we apply a dot product, so we will get d into ds cos theta. Okay, so it means electric flux is the dot product of d and ds. Okay, so applying the whole surface, we will get surface d dot ds. So we will get this equation psi is equal to d dot ds. Now the first example, rho l, we have given the rho l which is equal to 8 nanocoulomb per meter, and that is lying on the z axis. So we have to find the e and d for the point rho is equal to 3 meter. Okay, so as we know that e is equal to, so first we have to find the e. E is rho l over 2 pi epsilon naught rho a rho. So all the values are given. Rho L is 8 nanocoulomb per meter. Rho is given, that is 3 meter. So by putting these values, you will get E is 47.95 in the direction of arrow. Now simply by multiplying epsilon naught with E, we will get D. So D will be equal to, by putting these values, we will get D 0.424 nanocoulomb per meter. Okay, so this was very simple example, and now moving to the example number 2, the electric flux density in a region is given by d is given. This is in the form of r, theta, and rho. So it means sorry, r, theta, and phi. So it means d is in the form of what? Spherical coordinate system. So we are demanding the psi means the flux line, and z is greater than 0. This is the given region, and x square plus y square plus z square is equal to 36. Okay, so now this is actually this equation of circle. So equation of circle means uh, This is equal to r square or the rho square. So from this r will be equal to 6, means we have to take a square root on the both side. Okay, the given region is a half sphere because the given region is z is greater than 0. So z is less than, means negative z has not been given, or have to consider only the positive region. Okay, so theta will be equal to, and this is actually the semi-sphere. So for the limits for the semi-sphere is theta from 0 to pi by 2 and phi from 0 to 2 pi. Okay, so as we have to find the psi value, so this equation has been proved in the previous slides, so we will get use of this equation. As the differential area in the spherical coordinate system is ds, we have already studied the differential area in CCS, SCS and RCS in the previous lectures. So directly, so ds will be equal to this for the spherical coordinate system. Now first we have to find the dot product, and then we will apply the integration with their given limits. Okay, so this is d dot, this is ds. So applying the dot product, so first we will apply the dot product on the ar portion only, because the remaining portion will be 0 if we apply the dot product. So 10 times this, so 10 into this. Okay, so this is actually the dot product. Now we have to apply the integration. Okay, so 10 r square this. Okay, this is actually the dot product. Now the integration 10 r square sine theta d theta. Okay, the limits for theta are from 0 to pi by 2, and for the phi we have 0 to 2 pi. Okay, so and the r value is fixed, that is r square is given, that is 36. So later on we will put the value for the r square as 36. So applying the integration and putting the limits, upper limit minus lower limit, we will get this. Okay, so this was a simple example. Now this is another example in which t is given, the same given and required data as 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 in previous example. So d is but now here the d is given in a rectangular coordinate system. We have to find the psi value. Okay, and the given surface is x is equal to 3. Okay, which is fixed, and y is from 0 to 2. This is in the direction of y, so 0 to 2, and z from 0 to 1 on the z direction. Okay, while the x is fixed, that is 3. Okay, okay, after the psi we have to find the e absolute at p is equal to 3 to 1, means x is equal to 3, y is equal to 2, z is equal to 3. So uh, using this equation we have to find this psi. D dot ds, okay, this is actually the d given d, and ds in the rectangular coordinate system is dy dz. Okay, in the direction of ax. So uh, this is the x ax. So for the dot product I have already told you that we have to multiply only this the coefficients having the similar unit vectors, because if you multiply this with ay or az, it will become 0. Okay, so by multiplying these we will get y square z cube dy dz. Okay, from here. So the dot product has been done. Now the step is applying the integration with their given limits. So the limits for the z is from 0 to 2, and from 0 to 1, and for the y that is from 0 to 2. Okay, so this is the simple integration of z cube and y square. We will get psi. Okay, now you have to the d is given and we have to find e. Okay, so dividing d by epsilon naught, t is equal to this. Okay, so as we have to find the d at 3 to 1, so replacing 3 to 1, 3x y is equal to 2 and z is equal to 1, so this. Okay, so after putting these values we will get d is equal to this. Okay, now for the e, uh, dividing d by epsilon naught is 8.85 absolute permittivity into 10 to the minus 12. Okay, so we will get e, this is the e vector. Now to find the magnitude, so we will applying the square on each of the component, and then we will take the square root, we will get this. Okay, 4.31, very simple. Now the divergence theorem, what is the divergence theorem? Actually the divergence theorem, uh, we will discuss divergence theorem in the next slide. Okay, this is actually a relation, that is d dot ds, the closed loop d dot ds is equal to psi, and that is also equal to the del vector of d. Okay, and the volume del of d. Okay, this is actually the divergence theorem. Okay, so if we are demanding that we have to find uh, we have to prove the divergence theorem, it means that we have to prove that the answer from this and this will be equal. So by this way the divergence theorem will be proved. Okay, so we will discuss the divergence theorem and the numerical of the divergence theorem in the next slide. So thank you for the moment.